Okay, hello everybody. Just a little video on how to do the gizmos if people were a little lost. So the first part is atomic radius, and what you're going to do is you're going to measure the distance between the nucleus and the valence electron. So if you notice this column here, where's my pen? This column here, oh, that's ugly. It's all group one, okay? So this is group one. All of this is group one. And we didn't, francium's not included, but that's okay. This is group one elements. So what you're going to do is click on this box here, show ruler, and then connect this one end to the nucleus and the other end to the valence electron. Okay, since they're all group one, they all have one valence electron. Okay? Then click Save Radius. I already did that. That's why that 53 showed up. And when you collect the data, or it says collect data, use the ruler to measure the atomic radii of group 1 elements. As you do, count the energy level shown as rings of electrons in each atom. Record in the table. Okay, so you're going to record that in your table. So if you see there's one energy level, one ring for hydrogen. Right, hydrogen's done, 53 picometers. Lithium. Lithium has two rings, okay? And I see I'm connecting the ruler to the valence electron, two rings, so two energy levels. Okay, click Save Radius, 167. Sodium, three rings, three energy levels. Connect to the valence electron, Save Radius. So again, group one, only one valence electron. Potassium, okay, four energy levels. See how we're increasing energy levels? And as we increase in energy levels, the radius gets bigger. Okay, click Save Radius. See, you don't even have to move it from the middle anymore. You can just move it to the valence electron. So, oh, there's the bell. Excuse that for a second, please. So you can see how these numbers increase as you go down a group. Okay? These numbers are the atomic radii. The atomic radii increase as you go down a group. All right, what about if you go across a period? So you see on the bottom here, this says period 6. But the next question, or the next table you got to fill in, asks you about, starts with sodium. Okay, so we need to get to period 3. Sodium's in period 3. So click on sodium. Right? I just clicked on sodium and went to period 3. Now do the same thing. Okay, click on magnesium and the valence electron. It has two, just pick one. Okay, just pick one. So as you can see, we're increasing in valence electrons as we go from left to right. That's okay. Just pick the one that's all the way to the right. It's going to be the same. You can try it out for yourself and see if there's a difference, but it's going to be the same. So aluminum, Al, 118, silicon, 111, potassium, 98. So again, I want you to observe what is happening to the atomic radius. Look at these numbers at the bottom here. Okay? Look at those numbers at the bottom. What's happening? What's the trend you're seeing with those numbers? Again, these numbers represent the atomic radius. What about the number of protons? Okay? This table asks you for number of protons. You can also click on the element and it shows you the number of protons. Let me use a different color. I can't. That's okay. Oh, that's not the right one. You can use a different color. Let's use blue. So number of protons right here. Okay. So sodium has 11, magnesium has 12, aluminum 13, and you can see it's all going to increase by 1. Okay. So they want you to observe what happens to the radius as you move across a period. So that means from left to right, just like we read from left to right. Sodium, what's happening? Magnesium, what's the trend? What's the pattern that you're seeing, that you're noticing? Okay. And then I want you to, in complete sentences, explain why this trend occurs. So I'll go over it right now. So why is this trend occurring? Okay. So the number of protons is increasing in the nucleus, right? As we go from sodium all the way to argon. Sodium has 11, argon has 18. So those protons are pulling on those electrons to come closer and closer to the nucleus. So because the attraction is greater with the higher number of protons you have, it's going to decrease the radius. Okay, I'll say that one more time. So because the number of protons is increasing, it increases the force of attraction between the protons and the electrons, decreasing the atomic radius. So that's when you go across a group. I'm sorry, across a period, excuse me. So when you go from sodium all the way to argon. Okay, so that is atomic radius. What about ionization energy? So let's get back to group group one. So click on sodium. All right, sodium is in group one. Click on hydrogen, and then you're just gonna go move this. First, you're gonna move this atom. It's gonna stop once the electron gets pulled off. Click on show ruler, connect one end to the electron next to this positive charge, connect the other end to where this electron was, not on the nucleus. You're going to connect it to where it was, okay? And it's going to show you the length, which is the distance, and the ionization energy. You're going to do that for each one. I'll just do it real quick just to show you. And this show ruler only becomes visible when you displace that electron. That electron is removed. Okay. So the numbers that's recording here is the energy. And what is the trend that you're seeing with the energy, with those numbers as you go down the group? Excuse me. Keep saying period. Let me drink some coffee real quick. Okay, so what you're seeing is that the energy to pull off that electron, because that's what you're measuring right now, the energy to pull off that electron is getting smaller and smaller. And that's what you notice when I took those metals, I cut them up, and I put them in some water. You saw as I went from lithium to sodium to finally potassium, you saw a flame. So it wants to give up that electron so badly that it ignites the hydrogen gas that's escaping. Okay, so the trend you're seeing with ionization energy is that as you go down a group, as you go down this group here, the energy is decreasing. So what about when you go across a period? So again, we're going to go back to our friend sodium, and let's go across this period here. So sodium, it's already recorded for us. Click on magnesium. So I'm looking at the period, which is the bottom here. Okay, here's the period. All right, and I'm putting this where the electron was. So for ionization energy, you put the ruler where the electron was. It just shows you this ruler. Aluminum. Silicon. Okay, so what are you noticing about the energy? Is it taking more energy or less energy to pull off a valence electron? So the general trend you're going to see, it's going to take more energy to pull off that valence electron when you go across a period. Okay. So look, we go all from sodium, 496, argon, 1,521. Jeez. So it takes a lot of energy to pull off that electron from argon. So argon is holding on to that electron for dear life. Doesn't want it to go. Okay, so as we go across the period, the ionization energy increases. It takes more energy to pull out the electron. Think about it like Velcro that's really stuck on something and it's really hard to pull off. That's what it's like pulling off an electron from argon. And sodium, it's like, the Velcro is barely attached at all. It's touching like a little piece. Okay, so again, I hope this has been helpful. If you need any other help, please, I'm stressing, please come to office hours, okay? And I will see you in the next one.